Good morning, good afternoon, or good evening, depending upon where you are in the world, and welcome to today's webinar, Current Security Trends Affecting Flash Memory Design. Brought to you by Tech Online, Macronix, and broadcast by AspenCore. I'm Colleen Heckman. I'll be your moderator today. We have just a few brief announcements before we begin. First, the slides will advance automatically throughout the event. You may also download a copy of the slides by clicking on the paperclip icon at the bottom of your screen. You can participate in our Q&A session by asking questions at any time during this webinar. Just type your question into the Q&A text area and hit the submit button. If you're experiencing any technical problems, you can also type that issue into the Q&A text area and hit the submit button, and we'll be glad to offer one-on-one assistance. At this time, we also recommend you disable your pop-up blockers. I'd like to encourage our attendees to complete the feedback survey that's located on the right side of your console. Be sure to complete that before you log off today, and thank you in advance. And now, on to the presentation. Current security trends affecting flash memory designs. Discussing today's topic is Jim Yastik, Director, Technical Marketing at Macronix America. Jim is responsible for standards development, ecosystem, market, product, and business development at Macronix America. With 30-plus years of experience in high technology sector, his previous roles including engineering, product marketing management, and business development for organizations focused on semiconductor, communications, and embedded software markets. It's with great pleasure I am now going to hand things over to Jim to kick us off. So Jim, with that, it's with great pleasure I now hand things over to you. Take it away.
Thanks, Colleen. What I want to talk about today is really centered around flash memory. We want to talk about the trends that are really driving specific features that better protect these types of memories. And we want to talk about the objectives we're trying to achieve with use cases being targeted and the types of information that we want to try to keep secure. And then I want to talk about some security concepts that I think we need to consider that affect flash memory. And then secure flash security and other system security comparisons is a topic I think needs to be discussed. And we're going to use our product line to kind of outline what the general differences are that I think relate to the broader industry in terms of what is offered today. And then I want to finish with an application design scenario. I want to focus on edge computing and in this case a smart building device. And hopefully this will help tie everything that I've talked about previously together and give you a better understanding of what needs to be considered when choosing a memory device and trying to keep it secure. So what I'd like to start with are the trends driving a need for greater security on flash devices. It's well understood the growth of devices today globally and the data that's being generated and stored. So I'm not really going to spend a lot of time talking about that, but I want to talk about some key areas where we think greater security needs to be. AI continues to grow, and with that, the number of models. These models are very expensive to develop, and they really are the crown jewels for companies that develop them. And so security needs to be greater for that. And then with the current geopolitical environment as it is, foreign companies and countries are collecting data on their adversaries, and that data is being stored with the hope and expectation that at some point they're going to be able to break the encryption keys and get to that data. So whatever data we're storing today needs to be secured even more securely. And so because of that, there are greater security mandates by governments that need to be complied with to thwart, these attacks, whether they be corporate espionage or they be done by state actors trying to essentially attack other countries' infrastructure and manufacturing or military infrastructure and equipment. So what are the objectives in secure designs? Really, it comes down to integrity and confidentiality and authentication. With integrity, what we're really trying to do is maintain the integrity of stored data or data that's being transferred. And that can be done in a number of different ways that I list here on the right. But you're basically trying to protect the bus. You're trying to stop anti-cloning or the cloning of devices. And you're trying to keep adversaries from tampering with these memory devices. So that can be done in a number of different ways, which I'll get into later. And then confidentiality, you want to make sure that the confidentiality of this data remains confidential. So that's being done in, again, a number of different ways, but really it's being done through encryption and that data being stored in an encrypted way. And you need to be able to protect the bus to maintain confidentiality. And again, it's being done in a way that the data is being confidentially transferred in an encrypted fashion. And then authentication just means that you want to make sure that the devices that you're talking to are the devices that are supposed to be there. And again, I'll get into that later. But there are a number of ways to do that through secure identification and other techniques. So I've already mentioned some of the use cases for secure flash, but I want to mention a few others. One of them is an opportunity to lower the BOM cost. Today, you look at designs that frequently have these secure elements. These secure elements are essentially devices that help with the provisioning. They store keys. They also are involved in secure boot implementation. And so if you can have the memory device do that, well, you're going to be able to lower your BOM costs and have fewer devices in your design. And then these flash devices can, again, be involved in the enablement of secure provisioning and reprovisioning. And then if they have anti-tampering features, well, then it's going to make it much, much harder for somebody to take a peek into these memory devices. And in some cases, you'll have older designs that need to be updated. They don't want to update the whole design. They don't want to redesign it and create a new product. They basically just want to make some tweaks to their design to meet security standards. And in this case, they can add a security device. They can add a flash memory device with security features. And then some OS architectures require multiple sets of credentials. In fact, quite a few, even say greater than 4 kilobytes of credentials. And a good example of that would be automotive, these newer automotive vehicles that are storing a lot of keys and credentials. And then I think finally, firmware rollback and cloning, if the security features are built into the memory device, it can really help to thwart any sort of firmware rollback to a version of the firmware that is more vulnerable, and then cloning these devices as well. So I've given some examples of memory that can be stored, but I want to give a few others. I think the biggest example would be the storage of keys from credentials, and they could be passwords, encrypted keys, that sort of thing, used to support DRM. It could support a number of streaming devices. When you get into cars, for example, the latest cars that are being produced have a lot of different features that are being implemented. And if it's an ADAS type of vehicle, well, then it's storing maps and subscriptions and so forth. So there's a lot of information that's being stored, and it's a wide range of things. And going back to vehicles or even smart buildings, you can have biometrics that are being stored as well. And one thing that I didn't really mention in terms of financial or e-commerce information is that if thieves were able to get a hold of this data, which they do frequently, that can be used to steal from people and steal their assets. Next, I want to go into the key security concepts to consider. So let's start with the root of trust. This is a very important concept in security, and you basically want to be able to create a trusted execution environment. And you do that through a set of functions that are inherently trusted by the system or device to ensure the security. And it acts as a basis for creating a secure environment. And some examples that I have here, one of them is the boot path. So the boot path can't be interrupted, it can't be changed, it has to execute without interruption. And each phase of the boot is interlocked with the next one to create a chain of trust. And then before that even happens, really, you have the secure boot process, which verifies the software image even before it runs. And then you need to be able to lock down and create immutable locations in the memory that can't be modified. And one good example of that is being able to store cryptographic keys that are immutable. And then finally, a design that supports the secure key storage, so you're preventing unauthorized access to the keys. So the next important security concept that I want to talk about is strong device identity. And what really is built into this concept are four things. First is trust. You want to be able to authenticate before establishing trust and secure communication. And then you need privacy. So you need to be able to ensure encrypted and secure communications to protect sensitive information. And then safety. You need to be able to prevent malicious attacks in sensitive product environments. And then finally, integrity. You need to be able to verify device and data legitimacy for the device and for the data being communicated. Next, I want to talk about another important security concept, and that is public key infrastructure. It's a specification that's been around for decades, and it's commonly used. It's basically to build trust through verification and validation with an entity that's trusted. And so it's a combination of hardware, software, people, policies, and procedures necessary to create, manage, distribute, store, and revoke digital certificates. And these digital certificates, they're also known as public key certificates, are used to cryptographically link the ownership of a public key with the entity that owns it. And these certificate-based technologies help organizations establish trusted signatures, encryption, and identity between the systems, typically used to establish trust when provisioning software and over-the-air updates to connected devices. And these digital signatures or certificates are used to create chains of trust that the devices can authenticate the owner of the software. And a PKI allows OEMs to manage their connected devices over the entire life cycle. So let me give you an example of how we use PKI for device certification for supply chain protection. So my company, Maycronics, we have a hardware security manufacturing group, and we insert these certificates onto our secure flash devices. And we have two levels, which I'll show in the next slide. But basically, we provide the public keys, we store the private key on the device, and then we pass off the public keys to the chipset vendor. And the chipset vendor then validates our part on their device, and then they in turn pass that on to the end manufacturer for the provisioning. And then they can do the same. They can verify the second level certificate. So let's dig down a little deeper to see how PKI works. In this example, we're using a device certification for supply chain protection, and this is something that Macronix implements. On the left-hand side, we have a single-level authentication scheme, and on the right, we have two levels of authentication. So on the left-hand side, the single-level authentication scheme, our hardware security department, we create a key pair that is both private and public, and we provide the public key to the end customer, and then we take the private key and then we essentially encrypt the certificate and sign it or encrypt it with the private key to create the signature, and then we store that in the certificate. So that certificate can then be read by the customer, and by taking the public key, they can take and they can encrypt it and recreate the signature to verify that the certificate is correct. And once they have the certificate and verified it's correct, then they can trust that information in the certificate is correct. In the right-hand side, we've got a couple of entities involved because when we produce the part, we give it to the SoC vendor. The SoC vendor then builds a subsystem that then they provide to the OEM or ODM, and they build it into their product, and then they provision it. So in this case, it looks a lot like at the first level, it looks a lot like what's on the left-hand side. We produce the key pair, and then we provide the public key to the chipset vendor, and then we recreate the signature and the signature from the level one, and then the chipset vendor can then verify that by reading the certificate and verifying the signature themselves. And then what they do is when they verify that the certificate is correct, they can read the device public key from that signature, and then what they do is they pass that on to their OEM or ODM partner. Okay, and then you essentially repeat the same steps. So we provide a level 2 signature that has the device public key in it, and it also has the ephemeral public key that can be used by the OEM ODM to do their provisioning. And so once the OEM ODM verifies the signature is correct, then they can trust that the public key, the ephemeral key, is correct, and then they can use that for their provisioning. So that's basically how it works. It's very effective. So let's talk about Secure Boot next here. Secure Boot is a lot like PKI, and I'll explain in a second. But Secure Boot is a security standard that's been around a long time. And basically, the computer boots using only software trusted by the manufacturer. And so what it does is it checks the digital signature of boot software, including firmware drivers, operating systems, and applications against the database of trusted signatures during the boot process. So if a digital signature is missing or invalid, then the Secure Boot will prevent the software from loading, and therefore it'll just block unauthorized or malicious code. And so by establishing this train of trust from the firmware to the operating system, the Secure Boot helps to create a more secure computing environment, protecting against various types of malware or unauthorized access. And so these digital signatures are derived from a private key from the entity that did the provisioning, and then it produces public keys that then are programmed into the SoC or a secure element. And I'll talk about that next. So the way the Secure Boot validation works, the system firmware verifies the integrity before loading for execution. And the bootloader itself has the digital signatures, and again, it checks them against a trusted source. Well, the trusted source are the public keys that are stored. They're stored in a vault, a trusted vault. And so what it does is it reads out the code, like I said before, and then it creates a hash, and then it it encrypts the hash and then reproducing the signature and then comparing it with the signature that it has stored. So again, it stores the signatures and it stores the public keys. And then basically only signed and trusted software components are allowed to run. And if there's some sort of a problem, well then what will happen is it'll vector to safe code. It'll go into a safe operating mode, and what will happen there will really depend on the designer of the product. So I'll reiterate that in our case, we can actually do that validation internal to the flash memory. So in this case, we don't write out all this code, which could be a lot. It could save a lot of time by not having to do that. And in addition to that, you're not exposing all the code onto the bus. So it's actually a very valuable feature to have, and we think will do well in the market. So I want to conclude with Secure Boot and talk about the device recovery. So like I said before, if the signatures don't match, what's to be done? Basically, you go into a recovery mode. And there's a hidden recovery block that has safe code, and it essentially vectors to that code, and then it runs that code. And like I said before, it really depends on the design of the product, of what will happen next. Okay, but that's essentially how Secure Boot works. The last security concept that I want to talk about is sector and block protection. I've mentioned it previously, but essentially what it does, it allows for commonly used features to create immutable locations in memory to reinforce root of trust implementations or safe modes. And I think a good example of that is recovery code during the boot process, the secure boot process. So with Armor Boot, if we do the secure boot validation, we can vector internally to basically safe code that can be ran, and we can essentially try to recover from a malicious attack. Okay, and so I want to give an example. So with our Armor Boot, the status register protect bits, they basically provide permanent protection capability. The one-time programmable bit, once enabled, it protects designated blocks from being reprogrammed, and the block protect bits will be permanently locked. The data in the block secured by the block protect bits are permanently protected against modifications. And so this is a feature that's been around a long time and in the industry, and it's a very useful feature to have in a memory device. Next, let's talk about flash memory comparisons and product examples. So let's start with a high-level comparison of flash devices. The basic classes that I think are relevant are embedded flash, eFlash, or embedded flash, just standard external SPI flash devices, and then secure flash devices. And so if we look at the interface, embedded flash, as you probably know, is a wide bus by 64, 32 or 64. And then external SPI flash is SPI flash. And the same is true for secure flash. So it just has a standard SPI interface. And the density options for embedded flash are really quite low comparatively speaking. External SPI flash and secure flash have relatively high density options. And then if you look at information confidentiality or integrity or availability, availability means its ability to not be disrupted is actually quite strong for embedded flash. And if there are no design features added for external SPI flash, well then for those three categories are pretty weak. And then for secure flash, those areas are addressed and they are strong. want to start by showing some security features in flash memory from a historical standpoint. These are features that were built into or provided in the past, and don't really include, well, they somewhat include some features that we have today, but I just kind of want to show a historical perspective. From a hardware standpoint, it was limited to, I think, BGA package. If you had a BGA package, the baud grid array was hard to get to because it was underneath, the chip. It protected against probing. And then there were protection pins, either write or read protection for essentially creating immutable blocks, which I mentioned in my previous slide. And on software protection, again, there's software protection, software block protection, or protecting blocks with software, or either doing it permanently or temporarily. And it had unique IDs. It even had a password protect, so you had to issue a password before you could actually access the device, which really that's a feature that's not really used anymore. We don't really see it being used, but it was historically a feature that we provided. And then sanitization, so you could basically physically erase to prevent any data reuse. But let's move on to the features that I think are more relevant to today. So in terms of what is relevant today, I'd like to basically use our product line to kind of show you what you would typically find when you were shopping around for a secure flash device. In our case, if you look on the far left, L1, L plus L2, that's the PKI scheme that I spoke about earlier. And that's built into a product that we call Armor Authent, so authentication. And then as you move further to the right, the security solution gets more advanced and more substantial with replay protection and authentication for RPMC. RPMC is a security solution that is primarily used in the compute market, but you might find it used in other markets as well. And then going further right and further up to higher security levels is our Armor Boot. It offers replay protection and the Secure Boot update that I had mentioned to you before. The update being it can update, do, and support OTA type of operations, over-the-air operations. And then it has device recovery, which I spoke about, and then authentication. So the PKI authentication. And then our top of the line, our most advanced processor, our Armor Flash memory device, offers replay protection, but also secure storage. And what I mean by that is you can partition the memory to have various levels of security, from no security to authentication only to authentication and encryption. And then the channel itself between the SoC or the host and our device is encrypted, or you can encrypt or de-encrypt. So, and then it has anti-tampering features as well as the authentication scheme that I had mentioned before. So let's drill a little further down on the comparison. So if you look at the table here, if you read from the left to the right, Standard Flash, RPMC, Armor Boot, and Armor Flash, and then read down vertically, if you look at the interfaces, they all support standard SPI interfaces, and the VCC range is 1.8 to 3 volt. The key length right now we have 32 bytes, and then key provisioning for RPMC and Armor Boot are symmetric. Armor Flash is asymmetric. And then PUF, or the physically unclonable function, which essentially is a fingerprint that is intrinsic to each device, and it's unique. It's highly unique, which is commonly used today. We support that in our RPMC product, Armor Boot, and Armor Flash. And then the Armor Flash can produce a ESDSA digital signature if that's required, and Then the secure area is 4 megabits per zone, and this is the configurability I spoke about earlier, where you can partition memory and configure each zone to be various levels of security. And then you have an encrypted channel on the Armor Flash using the AES algorithm, and then authentication, we use the AES GCM or the HMAC authentication scheme. And then the Armor Flash, the MX78, has the true random number generator. It has the 3 secure flash devices have monotonic counters for replay protection and other security features. And then Armor Boot, as the name implies, supports secure boot. And then finally, our most advanced memory device supports, not supports, but has certifications for FIPS 142. We're in the process of getting the 143, and we support the ISO SA 21434. And I just want to show one more comparison with using standard flash as the baseline and then comparing that with Armor Boot. So again, you can kind of see some of the same parameters. Our range for this type of device, and the reason why I'm highlighting this comparison is that this is a part that we have, and that if you look into the market and you research flash memory devices that might fit your design, this is a particular type of device that fits a lot of use cases, and that's why I'm trying to highlight it here. The density range is 128 megabit to 1 gigabit, and you can see the VCC ranges that we have. And the interface can be a single, dual, quad, and coming soon a by 8, an octal interface. And you can see we support read interface speeds of 50 megahertz, and then up to 133 for certain modes. And we do support DTR, DDR mode. And then we do key sharing, HMAC key sharing as well. And then we have 2 monotonic counters. We also support the PUF, like I mentioned before. And we support authentication, authenticated lock, which essentially locks a block and you can't get to it unless you authenticate. So it's a pretty important feature to have. And then we have the boot code verification, which I mentioned before, followed by device recovery. And in terms of functional safety, we support ECC, and these are the packaging types that we support as well, WSON, SOP, or BGA. So let's just conclude this section by showing some pretty typical use cases. At the top here, you see secure OTA updates. So, these secure flash devices do a good job of supporting a secure update. Off to the lower left-hand side, you can see the flash device being used in automotive. So, for example, our high-end Armor flash device is typically found in the gateway, where it stores a lot of keys and credentials. So that model works well for that type of flash device. But in these ECUs, you could easily use Armor Boot. And then off to the right, for a fast secure boot, again, you could use the Armor Boot, is what I was mentioning before, in a number of applications. And so here we're showing, cameras, but it could be any type of embedded application. And now I would like to conclude with an example application. As I mentioned before, we're going to use a building sensor gateway as an example, and we're going to talk about security as it relates to secure flash. And I want to start with device provisioning, which we've talked about quite a bit already. But essentially, what happens when you're doing device provisioning? You're basically injecting security credentials. It could be software, it could be cryptography keys, data, it could be the recovery code that I mentioned before for secure boot. And you're putting that into secure memory. And semiconductor companies, secure programming houses, ODMs, OEMs, or even in the end customers could be doing this device provisioning. And so once that initial provisioning happens, the post-provisioning, you have unique device identities from certificates and private keys that need to be stored. So you have all these certificates, which I mentioned before, but you have, in addition to that, you have certificates maybe from a central authority for the device when it's being onboarded. And so these certificates and private keys, they're stored in secure memory. And then secure access methods, if you're going to be storing private keys onto memory, there needs to be secure access methods to do that. So, but ideally, identity private keys, they originate from the silicon and they never leave the device. So alternatively, identity keyed injection is done at the secure facility to ensure recovery code is locked and hidden. So once the provisioning stage is done, you're going to want to be able to bring the system up. And so you just need to make sure that the unit has the right memory device and it's uncorrupted software through an immutable boot process, so using secure boot. So you want to be able to authenticate with the device and then execute the secure boot. And you would basically authenticate the memory device through some symmetrical key sharing scheme, and then verify using a cryptographic signature verification, which I discussed before. And so if there are any mismatched digital signatures, then you want to vector to recovery code. If the unit's being onboarded, the previous step definitely has to happen prior to any flashing of new software. And the software image, it's checked via a hash algorithm, or it's signed by private keys and verified by the secure boot process. And then you want to utilize the public keys provisioned into the device to do that. So if it's going to be part of a larger network-based application where cloud service providers are involved, you're going to need to onboard that device to a cloud service like Amazon AWS, Microsoft Azure, Google Cloud. So one of these, regardless of which one you use, they're going to require secure communication channels between their servers and connected devices, and some of them require that the memory devices where their code, keys, certificates, and so forth are going to be stored. They need to verify that that the device is validated. And so, like I said, these channels need credentials and certificates to authenticate the connected device and to generate cryptographic keys for these encrypted data channels that are required. And lastly, let's finish by talking about lifecycle management. These certificates, they have expirations, and they can be revoked to enhance security. And this really helps to control the device connections to cloud services to make them safer. And if there's any vulnerability that's found, the certificates can be revoked, and it prevents the devices from connecting to the server. And these validity periods, and they ensure owners stay updated on threat developments. And cryptographic key rotation is actually pretty common, but it ensures that the keys remain secure and requiring certificate reissuances as well. So you're going to have through the life cycle, you're going to have continued over-the-air updates. You're going to have continued re-provisioning, I guess, of credentials, keys, and other information from these cloud service providers. And so there needs to be an onboarding process where the unit is retired to avoid any reverse engineering threat. So that's the conclusion of this webinar. And I hope you enjoyed it. I hope you found it informational. And if you have any questions, please please feel free to reach out to me or to our sales staff if you have any further questions. So Colleen, back up to you for Q&A.
Well, thank you, Jim, for an excellent presentation. To our audience, please don't go anywhere. We are now moving on to the question and answer portion of the event. So please go ahead and enter your questions in. We'll get to as many as we can. Jim, we've got a bunch coming in, so I hope you're ready, sir. Our first question asks, do I need any special software to interface to Armor Boot?
Yeah, you don't need any special software. We do provide example software, but it's a standard SPI interface with a command set. Obviously, it's a secure flash device, so it does have secure commands, but those secure commands, again, are easily programmable to support the features that Armor Boot offers. So, again, we can provide that software if you are doing a development.
Excellent. Thank you, Jim. Again, to our audience, if you have any questions, you can go ahead and submit them. We'll get to as many as we can. If we don't get to your individual question, someone will get back to you after the program is over. So the next question asks, regarding the authentication feature, just to be clear, Micronics has a provisioning group that can provide what I need to fulfill this feature?
Yeah, we have a group within our company. It's a highly secure group that does this provisioning, and it is a service we offer. So if you need authentication features, you need these certificates programmed in, our root keys programmed, we can provide that service.
Excellent. Thank you, Jim. Okay, moving along. This person asks, so if I have several signatures in my code image, how many signatures can I verify?
So what I think the question is referring to is Secure Boot. So Secure Boot has, the code image can be several sections, and so it can have multiple signatures that need to be verified, and we can verify up to 2 of those. If you need more than that, we'd like to hear about that. Thank you.
Excellent. Thank you. Sorry, I didn't mean to cut you off there. Thank you for that. Okay. And finally, our last question asks here, do you plan to support post-quantum computing requirements in the future?
Yeah, I think the short answer is yes, we are. We've been following this for some time, following the specs and the guidance that's been coming out of several foreign governments, in particular NIST in the U.S., and we are prepared to support this in a future version of our product.
Excellent. Thank you, Jim, for a great presentation and Q&A. To our audience, for more information related to today's webinar, please visit any of the resource links available in the paperclip icon at the bottom of the screen. Within the next 24 hours, you will receive a personalized follow-up email with details and a link to today's presentation on demand. So thank you for attending today's webinar, Current Security Trends Affecting Flash Memory Designs, brought to you by Tech Online and Micronics. This webinar is copyright 2025 by AspenCore. The presentation materials are owned by or copyright by Micronics, and the individual speaker is solely responsible for his content and opinion. On behalf of our guests, Micronics, I'm Colleen Heckman. Thank you, and we hope you have a great day.